So if you go back to the definition of absolute maximum and absolute minimum, if you go back and look at the definition, there's something real important in here. And that is in the inequality, do you see that it says that that point must be smaller than or equal to all other points on the function? And this says it has to be, for a maximum, it has to be greater than or equal to all other points on the function. So with the horizontal line, every point on that line gives you both the absolute max and absolute minimum. They're the same value. That answer your question? Okay. All right, so what we're talking about now is that if I draw it without picking up my pencil, right, then I have to achieve both an absolute max and min. Then I have a couple of little animations here to kind of help us see that. This is just me drawing, okay? There, I draw that curve, and when I do that, I'm going to have an absolute max, absolute min. So I label them absolute max, absolute min. Let me do a different picture here. Right, do that. Absolute max is the right end point, absolute min is the left, absolute min is this point, right? How about this one? Now that's a straight line but not horizontal, right? The absolute max is the right end point, absolute min is the left, right? How about this one?
On the one that goes straight up, the horizontal one, there is no local.
Where? The one I did before?
Because the only locals would be the endpoints?
Yeah, so for this, your locals would be the endpoints. But those are also your globals. Right. Yeah. What about that one? That one's what? Okay, so I cheated. I have to throw that out. I can't give you that picture because I picked up my pencil, right? That violates the theorem. So I can't go now and tell you to, show me where the maximum is. Yes?
I guess part of the definition says it's got to be on a closed interval to have an absolute max and min.
Yes.
If you went back that sine function and
Yes.
left it ongoing, wouldn't you still actually have an absolute max and min?
You could have one, but the theorem says you have to have them.
It says you have to have a closed interval.
No, the theorem says if you're a continuous function on a closed interval, then you have to have a max min.
Gotcha.
What you're saying is,
I'm not trying to limit. I mean, because if you left sine open and didn't close the interval, you would still actually have a global absolute max.
sure, there are some functions that don't have that strict of a requirement, where you just need the continuity maybe, and you don't have to have the restriction of a closed interval. But the theorem says that these are the conditions we have to have. Continuity and on a closed interval, then your guaranteed max and min is going to happen. Yes?
Would you split this into two?
I mean, you could look at it as two different pieces, and then, but the one on the left is not a closed interval because you can't. It's still not defined, right? It's not defined at that vertical asymptote.
Call it open interval on the left and then closed interval on the right.
But it depends on if it's defined there or not. I need the definition of the function, but you could possibly put a dot right there, and then you would have something on the right. What this is going to come down to for us is that, remember I said there's going to be like two ideas here, right? If we're on a closed interval, right? That was the first idea, was if we were on a closed interval. We have the closed interval method. Whenever we have that, we're always going to be able to find the absolute max and absolute min. We will be able to do that. But if we're on an open interval, the best we're going to be able to do are local maxes and local mins. We're going to be able to find the peaks and valleys on the function, right? Now we can use more analysis to figure out, is that the highest point? Yes, it is, but it'll be a little more we have to do. Yes?
Is there a note theorem because open and closed?
That's what I'm saying. On a closed interval, we're going to have a theorem and we're going to have a method. On an open interval, we're going to have a method.
Okay.
And it's going to be more involved, and like I said, it's not always going to give us the absolute max and absolute min. We're going to have to investigate a little bit more. So
You closed two open. Okay.
That's called a half open interval.
Okay.
So like if you had a graph that did this, started here and then did this, and then I put an arrow, that would be considered not closed. And if it's not closed, we can't use the closed interval method. We could use the other method, the open interval method. Okay, so now we have a theorem, another theorem, right? That first theorem just said that if you got continuity, closed interval, you've got to have a max and min, all right? Fermat's first theorem here says that if f has a local max or min at the point C and the derivative exists, then the derivative must be 0. So before I actually do this, I want to talk to you all a little bit about this, the concept of a theorem, all right? Most theorems have what's called the if statement and then the then statement. So something like this. If P, then Q. Most theorems are of that form. If these conditions are met, then here's the result. This theorem is saying if, right, what's the condition P? Well, if F has a local, right, max or min at some point C, right? That's the condition. And what else? What does it say? And the derivative exists. Remember, the derivative at the end of the day is a limit, right? And not all limits exist. This says that, say you've got a function that has a local max or a local min. King of the hill, right? King of the valley. If that's happening somewhere at some point, and the derivative there exists, then the theorem says, then you can conclude what? That the derivative must be 0. When you see statements like this in math, the order is important, all right? We cannot read this backwards. We cannot say if this is true, then this is true. That's not the way theorems work. It's this implies this. I'll give you the classic example that I give my classes. If you live in Texas, then you live in the United States. So I'm saying geographically, right? If I'm standing in Texas, then I'm standing in the United States, at least right now, right? Texas hasn't broken off from the United States yet, right? Okay, so right now, if I'm standing in Texas, I'm standing in the United States. That's a true statement, right? Does it work the other way around? If I'm standing in the United States, then I'm standing in Texas. Well, could I be? Yes, but this means that this needs to hold all the time. So if you're standing in the United States, let's say I'm in New York, then I'm not in Texas, right? So you cannot reverse the order of an if-then statement and have the equivalent statement. So here, the big danger with this theorem is that students will read it the wrong way. They'll say, oh, hey, look, anywhere the derivative is 0, I have a local max or min. That's the way they'll read it. You can't read it that way. This says if you have a local max or min and the derivative exists, then we can promise you that the derivative is 0. All right? So let me give you a visual of this. Let me draw something that has a local max. Okay, I'm going to draw a local max, and I'm going to make sure the derivative exists. Where do derivatives not exist?
At the ends of functions?
No, you can have a derivative at the end.
Asymptotes?
Asymptotes. Where else?
A couple of corners?
Corners or cusps.
Or jumps?
The jumps, right? Okay, so there was like a couple of things, right? So I'm going to draw you something where I have let's just do a local max, and my derivative exists. Okay? Do you all agree that at C I have a local maximum?
Yes.
Do you all agree that the derivative exists there? So I don't have a jump, I don't have vertical tangent, I don't have a cusp or a corner, right?
Correct.
Yeah. So are these conditions satisfied? Yes?
Yes.
Is that true also? Yes. The derivative there is 0, right? You see the tangent line there? Is 0. Can anybody here draw me a curve that would have a local max, the derivative exists, and this not happen? You can try all day, try the rest of your life, it's not going to happen. I mean, that's why it's a theorem. There's no way to draw a curve where you're going to have this true and that not be true. Okay? All right, so that's nice. The theorem's nice. And we're going to use that theorem in a kind of a strange way. So that's just me saying be careful the order in which you look at this theorem. You know, you have to read it properly. Don't misuse it. Now we have a very important definition, a critical number. All right. So this is a definition. We need to all know what this means now. A critical number of a function. So I give you a function, right? And I go tell you, hey, what are the critical numbers of this function? What they are any numbers you can find where the derivative is either 0 or the derivative doesn't exist. Those are called the critical numbers of a function. So that means that if I give you a function, I say, hey, go find me the critical numbers, what you're going to have to do is find the derivative of the function and set it equal to 0. Solve that equation. And that's going to be your critical numbers. Then you're going to look at the derivative and ask yourself where it doesn't exist. And those are also going to be critical numbers. All right? Let's do an example. Oh. We'll do an easy one first. F of x equals 3x squared minus 5x plus 1. Okay? I want to know what the critical numbers are. Now, you might be asking, why do we need the critical numbers? What are they, why are they important, right? Let's just make sure we know how to find them first. Then I'll tell you why we need them, all right? So find the critical numbers. So what am I going to do? I'm going to take derivative, and I'm going to do two things. I'm going to take derivative, I'm going to set it equal to 0. I'm going to take derivative, and I'm going to figure out where it doesn't exist, right? I'm going to ask myself these two questions. But that means I need the derivative, right? All right, well, I gave you an easy function, take a derivative, right? Derivative of this is what? 6x minus 5 equals 0, right? I set it equal to 0. Can you solve that equation? Yeah, that's a linear equation, right? X equals 5 over 6. That's your first critical number. Now, there's something in this definition. Let me read it. A critical number of a function, f, is a number c, what does it say after that? In the domain of f. So this answer I get for me to call it a critical number, this answer must be in the domain of the original function. Now, when we look at this original function, that's a polynomial, and the domain of that's all real numbers, right? So this is definitely going to be in the domain of that, because that's domain has everything in it. So that is, yes, a critical number. Got it? Over here, I ask myself, where does the derivative not exist? So let's look at the derivative. Here's the derivative. It was 6x minus 5, right? When I'm asking where this doesn't exist, I'm asking, are there any numbers I can't plug into this? Is there anything that I'm going to plug in and it's going to be undefined? No, right? There's no issues here. This is a polynomial. It's a line. It's a well-behaved function. So this question of does not exist really comes down to what's the domain of this? Is there any problems with the domain? Right? That's the question. And here, nothing, right? So basically, I can omit this. We only have one critical number. Do another example. How are we doing on time? 20 minutes? All right. So what if we take f of x, let's go 3x to the 4th minus 8x cubed. That's a little more complicated. Find the critical numbers. Same instructions. So look, aren't we going to need the derivative? Okay, we may as well just get the derivative right now. Derivative of that function is what? 12x cubed minus 24x squared, right? That's my derivative. Now I'm going to figure out where's that derivative 0 where's f prime equal to 0? And then this one, I want to know where f prime doesn't exist. All right, so take that derivative, 12x cubed minus 24x squared, set it equal to 0. And this right here may look bad, but it's just a polynomial, and I made it so that it factors GCF first. What's GCF of this? You can pull out a 12 and an x squared, and that leaves you with x minus 2 equals 0. And then you set both of those equal to 0, and you get two solutions, right? 0 and 2. You know, we've been doing these problems all semester, and we've been doing raw derivative. And I told you at some point, I said, please be looking at your answers, compare them to the back of the book, try and make your answers look like the back of the book, because at some point you're going to have to set these derivatives equal to 0, right? And then do algebra. So the day has come, right? The day has come. So just be prepared. You're going to have to start doing something with this derivative now. So I have two critical numbers, I think. I need to make sure these numbers are in the domain of this. Well, this domain is everything, right? The domain of this, domain of f, the original function, is negative infinity to infinity. So no matter what answer I get here, it's going to be a critical number. Does the derivative never exist? Is there anything I can plug in here to cause a problem? No, it's polynomial, right? So it doesn't apply. You with me? Let's do one more. How about, can I erase? Yes, we're good. How about find the critical numbers f of x equals the square root of x. Right, I'm going to need the derivative, right? So may as well find it now. Derivative of this function, 1 over 2 root x, right? Now I want to know where's that 0, and I want to know where that doesn't exist. So where is this equal to 0? Well, where does 1 over 2 root x, where does it equal 0? So I'm gonna put something on the board here. First time I put this on the board. This is a little side note for us. If you ever have a fraction, a over b, equal to 0, right? So if you're ever trying to solve where you have a fraction equal to 0, then all you ever have to do is look at where the top is 0. In other words, what I'm saying here is that the only way a fraction can ever be 0 is if the numerator is 0. Because if you start with the fraction, couldn't I always multiply both sides by b here? Couldn't I just multiply this by b, multiply that by b, 0 times b is 0, and then the b's cancel here and I get a. So no matter what, if anyone ever gives me a fraction, they say, hey, when's that fraction 0? I can just look at the top and ask that question, when's the top 0? So is this ever 0? Well, that would mean the top would have to be 0, right? But that's not true, right? That's never going to happen. So there's no value of x I could ever plug into this to make this true. So there's no critical numbers from this. How about over here? If I look at my derivative, are there any values of x that I can't plug in? Can't plug negatives in, right? Because you can't take square root of a negative. But wait a minute, wasn't that the domain of the original function? Hold on, look at the domain of this. What's the domain of this? 0 to, right? You can plug 0 into this, can't you? This is, the domain of that is 0 to infinity, right? Because the square root of 0 is 0. Then you can only plug in positive numbers. So this is the domain of the original function. The domain of f is bracket 0 to infinity, right? The derivative, yeah, that's right. You cannot have a negative down here, right? Or 0. You can't have 0 here, right? So I only have one critical number. What is it? 0. 0 is the only critical number. The reason it's the only critical number is because it's the only number I can't plug into this that is in the original domain. Right? 0 can go into this, right? 0 cannot go into this. Negatives can't go in here, right? Right? Negatives can't, but negatives can't go in here. So I'm not even going to consider negatives as critical numbers. If you look at the graph of square root of x, look at the graph of that function. This is the graph, right? That's the graph of the square root of x. Do you all see why we have a critical number at 0? Yeah, our tangent line is becoming vertical. And so our derivative is becoming a vertical tangent, which means that the derivative doesn't exist there. Okay, y'all get the basic idea of what a critical number is? You take the derivative of the function, set it equal to 0, figure out where it doesn't exist, and then you got to play with some domains. You be real careful with the domains. Now, we get a new theorem. It's a revised version of Fermat's theorem. It says if f has a local max or min at the point C, right? If f has a local max or a local min at the point C, then C must be a critical number of f. See, this is like the previous theorem, but it's not saying that the derivative would be 0. It's saying that that we would have a critical number there, which means the derivative is either 0 there or the derivative doesn't exist there. It's one of those two things is happening. This is the most important note today, right here. This is it. This is what I refer to as the closed interval method. How to find the absolute maximum minimum values of that should be a continuous function, a function on a closed interval. So I'm going to open that note up and I'm going to read it out to you, and then we're going to do hopefully one problem before we go. It's a little too big. All right. I'm just going to read it first, and then we'll go through a problem. So to find the absolute maximum and absolute minimum values of a continuous function on a closed interval. Remember, we said if it was continuous on a closed interval, it has to have a max, absolute max, it has to have an absolute min, right? This is saying to find those 2 points, or 2 values, the first thing we're going to do is find the critical numbers of the function. We're going to find the critical numbers. And then we're going to evaluate the function f at those critical numbers. So whatever answers we get here, we're going to plug those answers into the original function. And then we're going to evaluate the function at the 2 endpoints. And then we're going to compare all those answers, and the biggest answer we get out will be our absolute max, and the smallest we get will be our absolute min. That's it. So it's like this. You start with the function, right? Oh, sorry. You start with the function, and then what we're going to do is we're going to take the derivative of it. We're going to set that derivative equal to 0. We're going to figure out where it doesn't exist. And we're going to get answers from this, right? We're going to take those answers, and we're going to plug them into the function. And that's going to give us points on the graph, isn't it? So what we're doing is we're saying, okay, between A and B, we're going to find these critical numbers, whatever they are. I'll call the first one maybe C1, C2, C3. Let's say these are our critical numbers that we found. We plug them into the original function, and those are just going to be points, right? So maybe it gives me that point. Maybe this one gives me that point. Maybe this one gives me that point, right? And then I take the endpoints, that's the second step, and I plug those into the function. And maybe this one comes out here, and maybe this one comes out here. That's all you need to find the absolute max or min. The absolute max or min is either going to occur at the endpoints or it's going to occur at one of the critical numbers. So can you all see where the absolute max would be here? It'd be this one, right? Yeah. That'd be your max. And then the minimum would be this point, which is nice. I mean, this is a major point in this class, because what we've said is that if you give me any function on a closed interval, as long as it's continuous, in order for me to find the highest and lowest points, I only have to consider the two endpoints and then where the derivative is 0 and then where the derivative doesn't exist. That's all I have to consider. All the other points are irrelevant. All right? So let's do one. Got 10 minutes. Y'all doing all right?
Yep.
Is that what I heard? I'm gonna pull one out of the book here. We're in 4.1. Did you say, oh God? All right, let's do f of x equals x over x squared minus x plus 1 on the interval 0, 3. Now I want you to just take a step back and appreciate what I'm asking you to do here. All right? I'm giving you a rational function, right? And I'm asking you to tell me if you were to look at all the numbers between 0 and 3, right? There's an infinite number of numbers in here. If you were to start plugging those values in here, what's the biggest value you ever get out? And then what's the lowest value? That seems like a very difficult question for us to be able to answer, right? By just guessing. But we have a method now. We can find the biggest value that will come out and the smallest value that will come out on this interval. So long as what? This is a continuous function, right? On the closed interval, we're good. So is this a continuous function on that interval or not? Does that function have any domain issues? Maybe we should start with talking about the domain of that. What's the domain of that function before we even do a derivative? Where would we ever have a problem? If what happened? If the denominator was 0, right? So let me just look at that real quick. I need to make sure that this would never be 0, right? We want to make sure that's never 0. Let's make sure that it doesn't happen. Does that have a solution? Does that have solutions? Possibly, right? And I just got to make sure none of those solutions are in here. Because if one of those solutions is in here, then I have a discontinuity, and the theorem and the method would fall apart. Make sense? So how do you solve that equation? Okay. And then? How? Oh, can't do that. Can't do that.
We gotta get one to the other side.
How, what do you mean?
Just subtract.
It's a quadratic. With quadratics, we always want to make it equal 0.
Oh.
Right? Look, I'm going to put something up here. And that's not this problem, but be careful. You cannot do this. I see this happen a lot. You cannot do that, and then that, and then tell me that x is 4 and x minus 1 is 4. I don't know if that's what you were going to do, but you can't do this. You can't move the 4 over here, take that, factor an x out, and then set each of these equal to 4. You can only do that if this side is 0. Then you can set each one equal to 0. Yeah. But it's a quadratic, right? How do we solve quadratics? Yeah, we either factor it or we use a quadratic formula, right? One or the other. So I don't have this will not factor, okay? It won't. So I'm going to have to use quadratic formula. Quadratic formula is x equals negative b plus or minus the b square root of b squared minus 4ac all over 2a, right? Does all look familiar? Why are you shaking your head? Huh?
I hate that.
You hate that? Really?
But it's all going to be one, right?
They're all ones. Well, that's a negative one in the middle, right? So be careful. So this is going to be negative b. This is b, right? Do I need to say that? That's a, that's b, that's c. So it's going to be negative, negative 1 plus or minus the square root of negative 1 squared minus 4 times a, which was 1, times c, which is 1. All of this divided by 2 times 1. All I'm doing this for is to make sure that this qualifies as a continuous function on a closed interval. I'm worried that the bottom might be 0 in this interval. So I'm just ruling it out. And do y'all see why I can rule it out? What happens in here? I get a negative under here, don't I? So you're trying to take the square root of a negative number, which is not a real number. So this has no real solutions, which means that I don't have to worry about any domain issues, ever, actually. Not only in here, but ever. This never has a division by 0. Right? So this right here turns out to be 1 minus 4, which is negative 3. And since it's negative, we can't take the square root. Understand? 1, take away 4. Negative 3, take the square root. Can't do it.
So
Yeah?
because we can take the square root, it's
No solution. No, this equation has no real number solutions. If you want to start talking about imaginary numbers, it does, but we're not doing imaginary.
but you're saying that we don't have any worries of 0 on the bottom?
That's-
because-
That's right. I was concerned that this might be 0 on the bottom. I was concerned about that, right? So I went to check, is it ever 0? And I said, no, there's no solution. There's no x's that will make that 0. So I'm happy. I mean, let's say we did this and this said, let's say we got 2 answers. It said 6 and negative 1. I wouldn't care because 6 negative 1 is not in here. So I would continue. Now, if I got this and it said 2 is a solution, I couldn't use this method because I have a discontinuity inside here. That's not going to happen to you, okay? I'm not going to give you a problem on a test where I give you this and then I intentionally make it discontinuous there. But you have to check. You have to know, right? Okay, we continue. I need the derivative, right? Because what I'm going to do, I'm trying to find the critical numbers. So I'm going to find now the critical numbers. Running out of time. So what's my derivative? I'm going to need it. Quotient rule. Derivative of top times the bottom minus derivative of the bottom times the top all over the bottom squared.
It's not like L'Hopital where it takes the derivative of the top and the bottom. This
No.
as a whole.
L'Hopital is only when we're taking limits, right? We are taking a derivative of a quotient, so we must apply the quotient rule. So, yes, quotient rule. So what do we get here? On the top, see, there's no more raw derivatives. We're going to have to set this equal to 0. So x squared minus x plus 1, that's this. And then here I'll distribute this through. So that'll give me 2x squared minus x, but then I have to subtract. So minus 2x squared plus x all over. Do not square this. Let's just leave this alone. Is that okay?